So what all did you learn this week? So a summary in this week. Firstly, you saw, yeah, you saw the notion of complete and co-complete categories. So what is a complete category? A category in which all limits exist or all small limits exist is called a complete category, and dually for a co-complete category is one in which all small co-limits exist, right? And calling it by this name is pretty natural, right? Complete and co-complete. So you saw examples of complete and co-complete categories. What else? Then you saw three different notions in which functors interact with limits and co-limits, right? So three notions regarding the interaction of functors with limits and co-limits. So what are they? First one is the obvious one. A functor is to be thought of as a transformation of one category into another, right? So it's very natural to expect that a functor should be able to preserve something, right? So the first notion is of preservation of limits. So it's a property that a functor may or may not possess. Many functors don't preserve limits, many functors do preserve them. Many functors preserve certain kinds of limits, not all of them, etc. So those go by a special name. Functors which preserve all small limits are called continuous functors, right? And functors which preserve small co-limits are called co-continuous functors. So it's like, have you ever, have any of you studied metric spaces previously? Okay. So the name is sort of after after what you see for metric spaces. So metric spaces in which every sequence which is supposed to have a limit, every Cauchy sequence has a limit, is called a complete metric space. So in the same way, a complete category is one in which all limits exist, and function from one space to another space is called a continuous function if it preserves limits in a certain way. I mean, what I mean is, for any sequence xn which converges to x in x, the sequence fxn should converge to f of x. In the same way, a functor will be called a continuous functor if it preserves all limits. So in other words, roughly speaking, this is not exactly the actual definition of continuous functor, but the idea is you should be able so think of a functor as like an operation, right? So a functor is an operation. Similarly, taking the limit of some diagram is also an operation. So what the idea behind what the idea behind preservation of limits or co-limits is that a functor will preserve limits or co-limits if it doesn't matter in which you do these operations. I mean, you can first, starting with the diagram, you can first take its limit, then apply the functor operation, or you can first apply the functor operation to the diagram to obtain a new diagram in the codomain category, and then take the limit. So these two commute in a certain way. That is, roughly speaking, the idea of preservation. Then you saw reflection of limits. So reflection and preservation are like, I mean, talk about, are concerned about properties. Some cone is a limit cone. This property of a cone to be a limit cone is exactly what preservation and reflection are concerned about, right? So a functor is said to reflect limits or co-limits if you start with a diagram in your domain category and with a cone in your domain category whose image under the functor is a limit cone. The image will always be a cone, no doubt about that. If you take a functor from this category into this category F, if you take a diagram in your category D, let's say, and if you take a cone on this diagram, then the image of this diagram will always be a cone in the image diagram. So this is F compose D. Take the image. So let's say this is A, this will be FA, and take the image of all the arrows. So this will again be a cone, no surprise about that. But a functor is said to reflect limits if whenever this cone, this image cone is a limit cone, that should imply that the original cone that you started with was a limit cone, right? So it's like for preservation you have an implication only in the forward direction, and for reflection you have an implication in the only in the opposite direction. So what does preservation mean? F will preserve limits if whenever you take a diagram D, right, and take a cone on this diagram, which is this, if this cone is a limit cone, if you know from before that this is a limit cone, then the image cone that you have here, the image will again be a cone, of course. The image cone should also be a limit cone. This is what preservation of limits means, right? In other words, a functor which takes limits to limits is said to preserve limits, which takes limit cones to limit cones. So preservation and reflection are just, in a certain sense, dual notions of each other. Preservation only is concerned about the forward direction, and implication is only concerned about the backward direction. And these are concerned about properties of a cone. A cone being a limit cone or a cone being a co-limit cone. This is what preservation and reflection are concerned about. On the other hand, there is also a further notion of creation of limits, which is like a very powerful idea, which not only just talks about the property of a cone being a limit cone or etc., it in fact creates cones which are limits. So a functor from a category C to a category D will be said to create, let's say, limits if you start with any diagram in your domain category C, let's call it D. Take the image diagram F compose D. The idea is that if this image diagram has a limit, some limit, right, then your original diagram should also have a limit, and this limit cone should get mapped onto that specified limit cone or something isomorphic to that specified limit cone. Now in literature there are various different ways to define creation of limits, etc. What I just described to you is something called strong creation of limits. Again, there is something called creation of limits, which roughly goes like this. So you start with a diagram D and assume that your image diagram F compose D has some limit. Then there should exist some cone on your original diagram D whose image under the functor F is a limit cone on the diagram F compose D, on the image diagram F compose D. And not only so, what further thing that you should have is that any such cone on your original diagram D which gets mapped to some limit cone on F compose D should itself be a limit cone. So it's a bit involved definition. People often refer to the first one as creation of limits. Sometimes people also refer to this notion as creation of limits. The idea is that the functor should be able to create cones which are limit cones in its domain. Okay. And by creating cones, what I mean is that if you start with any limit cone on your image diagram, there should exist a cone on your original diagram D which gets mapped onto something isomorphic to that limit cone. So in a sense, the functor creates limits over I mean it creates cones which are limit cones on the original diagram T. Creates, that is where the name comes from. Yeah, so this is the notion of creation of limits, co-limits. I'm sure you have seen examples this week, and even yeah, you also saw about the description of limits and co-limits in functor categories. So the idea is I mean, this is just the slogan. The slogan is that limits and co-limits of diagrams in functor categories are computed object wise or point wise. Sometimes people like to call it point wise. It's the same thing. So this is your slogan. Oops. Right. So in other words, or roughly speaking, if you take some functor category A comma B, and if you take a diagram in your functor category, so which will be a diagram of functors and natural transformations, let's say if I, if j, if k, and so on, together with natural transformations alpha, beta, etc., etc., let's say some gamma, etc., whatever, to compute the limit of this diagram, if it exists at all, should also be a functor, right? It should be an object of the functor category, so it should be a functor as well. How do you compute the limit? It's pretty simple. You just focus on one particular object on your domain, let's say A, and evaluate all these functors on this object A, or rather evaluate this diagram on this object A. So now you have a diagram fi A, fj A, fk A in the category B, right? Now this diagram in the category, and this should be alpha A, the component of the natural transformation alpha at the object A. This is beta at A, this is gamma at A, let's say. This diagram in the category B should have a limit. You compute that limit. If at every object A, I mean, I should say it like this: if at every object A this evaluated diagram at the object A has a limit, then your original functor should have a limit, and it should send A to the limit of this evaluated diagram. That is the idea. So limits and co-limits in functor categories are computed object wise. Whenever you have a diagram of functors, just focus on, I mean, just evaluate them at each object of the domain. So obtain a diagram in your category B, find out if this diagram has a limit. If for each object A in your domain category this evaluated diagram has a limit, then the original diagram of functors and natural transformations will have a limit, and it will be given in this way, or yeah. In fact, I mean, what I am just saying is can be stated more precisely in terms of the evaluation functors, but this is just to give you the idea. And what else? Yeah, the most important thing that you learned is about adjunctions. Perhaps one of the most important things that you learned this week. So adjunctions are sort of ubiquitous in mathematics. I'm pretty sure you have heard this line. They are almost everywhere, and the idea is pretty simple. So you take two categories A and B, and you take two functors now going in opposite directions. So f is a functor from A to B, g is a functor from B into A, right? An adjunction between f and g is a special kind of relationship between these two functors f and g, where we'll say the functor f is left adjoint and the functor g is right adjoint if you have this natural isomorphism of Hom sets, right? So if there is a natural bijection from B fa comma B onto a comma gb, right? This is the exact idea of an adjunction, right? So think of it in this way, that given two functors f and g in opposite directions, we'll say that there is an adjunction between them, with f being the left adjoint and g being the right adjoint. If arrows in your category B from the object FA to the object B are essentially the same thing, are the same as arrows from A to GB. So this is in B and this is in A. This is the idea. So these two functors f and g are sort of related in a very nice way, right? So notice that I have f here on the left, that is arrows are coming out of f, and I have g here on the right, so arrows are going into g. This is the reason for using the qualifiers left and right. So f is being applied on the left of the comma, that is why f is called a left adjoint. G is being applied on the right of the comma, so g is called a right adjoint, right? So f will be left adjoint and hence g will be right adjoint if you have a natural bijection. The word natural is really important here. It's not just a bijection for each a in A and B in B. The bijection should be in fact be natural, right? So what I mean by this is that if I take any other A prime object in A and B prime object in B, then this bijection, there will be a bijection by our assumption. This bijection should be defined in the same way as this bijection was defined. Okay, I mean, in other words, you should have a natural isomorphism from one functor to another functor. To be precise, what are those functors? So yeah, f will be called the left adjoint here of the adjunction, and g will be called the right adjoint of the adjunction, right? If this holds naturally in A and B in B, right? And this is what the idea is. And an adjunction between f and g with f on the left, I mean with f being the left adjoint, and g being the right adjoint, is exactly a natural isomorphism, or rather a choice of a natural isomorphism, is a choice of a natural isomorphism from this functor b f of dash comma dash to this functor. I mean, it really doesn't matter since it's supposed to be an isomorphism. So I could also say from you have an isomorphism from this functor a dash comma g of dash to b f dash comma dash. That really doesn't matter. The point is you should have a chosen natural isomorphism. This chosen natural isomorphism will exactly be called an adjunction between the functors f and g, with f on the left because f is being applied on the left of the comma, and with g on the right because g is being applied on the right of the comma. Okay, this is what the idea of an adjunction is. So usually we will always denote, I mean, given an adjunction, we'll always denote the left adjoint by f and we'll always denote the right adjoint by g. Okay, so let's move on to the problems this week. They are supposed to be simple. I hope they are simple, but let's see. Yeah, I forgot to introduce myself again. I am Shubhojit. I'm a PhD student at the Department of Mathematics in IISc, and this is week 5 of NPTEL. Okay. By the way, I think I mentioned, yeah. So so the idea is whenever you have an adjunction between two functors, so there is one functor which is the left adjoint, we'll denote it by F, and there is one functor which is the right adjoint, which we'll denote by G. I'll write this, I mean, the usual way to write this is this. So you use a turnstile symbol here, F turnstile G. Okay, so F will be the left adjoint and G will be the right adjoint. This is the way to write an adjunction, to denote that F is the left adjoint of the adjunction and G is the right adjoint of the adjunction. Okay, yeah. So you start with an adjunction between two functors F and G, where F is the left adjoint as you can see in the symbol and G is the right adjoint. Now of course we have seen this previously many times, that given a functor F from a category A to a category B, there is a functor F op from the category A op to the category B op, and there is a functor G, and since G is also a functor from B to A, there is a functor G op from B op to A op. So given F and G, you have these two functors F op and G op. The idea is to show that if F and G were part of an adjunction where F is the left adjoint and G is the right adjoint, then F op, there is an adjunction between F op and G op as well, with F op being the right adjoint and G op being the left adjoint. Okay, so we'll let's try to do this, but before that let's just quickly recall what this op notation here means. I mean, you of course know that for categories it denotes opposite categories. So given a functor, let's say S, from a category C to a category D, the functor so this is also another functor, S op from C op to D op is defined in a particular way. Don't confuse it with the usual way of defining the opposite category of a category. It's not that S op is, by S op I don't mean that the corresponding arrow in the category C comma D op, because that would have a change in direction, right? And that would not be a functor, that would just be a formal arrow, because as I have mentioned previously many times, the construction of opposite categories does not assign any meaning to the arrows. It's just a category theory construction, right? So though that particular arrow is op, I mean, whenever you are talking about this, should just refer to an arrow from D to C in the opposite category. That is something different. Here this op notation on S, this S op actually denotes a functor. If you are confused, we can also go with another notation like S hat, let's say. That really doesn't matter, but I hope that you aren't. So here S op is actually a functor, and how is it defined? So take any C, it sends it to the object SC. S was a functor, so S applied on C makes sense as an object in D. That is your object SC. Take an object C prime, it sends it to SC prime, right? Take an arrow. So note that this your domain category is C op, right? The opposite category of C. So an arrow in C op should be written as F op, right? Corresponding to some arrow F from C prime to C in C. So you take an arrow F op from C to C prime and you map it where? So F op is an arrow from C to C prime in your category C op. That means F is an arrow from C prime to C in your original category C. S was a functor from C to D, which means that there is an arrow SF from SC prime to SC in your category D. But what you want really is an arrow in D op. So again you apply, I mean, look at the corresponding arrow in D op. So that arrow will be SF op, which is now an arrow from SC prime to SC. This is your SF op. Okay, sorry, what? Yeah, I'm sorry. Yeah, SF op should be from SC to SC prime in D op. Okay, so by C op and D op, here I mean the usual opposite categories of C and D. The notation S op is just a new notation. We have seen this previously. It's just another functor. That's all. So this is just the definition that will help us in this problem. And we have seen this previously, so I'll just mention a recall here. So recall, yeah. Okay, so let's dive into the problem actually. So what is given to you? You are you are already given that you are given an adjunction. So f is a functor from what categories did I use? A. So from A to B, and this is left adjoint to the functor G from B to A. This is your adjunction. You need to show that there is an adjunction from, I mean, you need to show that there is an adjunction f between f op, which is from A op to B op. So we want an adjunction and between these two functors f op and g op. But now in this adjunction the f op becomes a right adjoint and the g op becomes a left adjoint. Oops. Yeah. We want such an adjunction, right? Now, I mean, again we could go step by step, prove naturality. I mean, first of all obtain a bijection at the level of home sets, then try to prove naturality. But you can check the naturality part, but keep in mind that, as I have already been mentioning, naturality is perhaps one of the most important things in the notion of an adjunction. Okay, that bijection that you have at the level of home sets for each ordered pair A of objects A in A and B in B, that bijection should be natural in both variables. That is, you should have a natural isomorphism at the level of those two functors. This naturality is perhaps the most important thing here in the definition of an adjunction. But please do check this. But for now, let's try to prove that there is indeed a bijection. So take some object A in A op, some object B in B op. What we want to show is that f op should be right adjoint to g op, right? So what we want to show is that A op of, so g op is supposed to be the left adjoint, we have to apply it on the left of the comma. So g op of B comma A should be in bijection with B op. So B stays as it is, B is now isolated. This g op should go there in the form of f op. So B comma f op of A. This is the idea of an adjunction, right? Whenever you have an adjunction between two functors f and g, you can literally switch. So if you have B fa comma B, you should be able to get to A comma GB. This is the idea of an adjunction, right? Where f is the left adjoint and g is the right adjoint. So you can sort of take f to the other side in the form of g. That is the idea of an adjunction. Yeah, so you have this. We should have this. That is the idea. So tell me, how can we get to this? How do we prove this? That there is indeed a bijection. So what was the definition of the functor S op? It sends an object C to SC. So in other words, by definition, S op applied on an object C is just the same as the object SC. So I can write this by using our definition of op functors, that this is equal to A op of G op of B is just GB, comma the object A, right? Am I audible, by the way? I just want to clarify.
Yes, sir.
Yeah, okay. So A op of GB comma A. Now tell me, you are talking about this home set of arrows in the direction from GB to A in the opposite category of A. So what is this equal to? So you are talking about the home set A of GB comma A, right? All arrows in A op from GB to A. What is this?
It will be equal to its dual, that is B of
No,
A
no, no,
comma.
no, 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 no. we don't know anything about duality right now. What we just know is A and A up are duals. So yeah, continue. This should be equal to.
B up, then
No, why?
G.
How do you get B up out of nowhere from this? You just have A up. We want to show this, right? Now A and A up are opposite categories. So you are given this Hom set A up GB comma A. What can I write instead of this? In terms of the category A, I mean, can I replace this Hom set in the category A up by a Hom set in the category A?
Sure, yes.
What is that? It should be equal to. So given a category A, how exactly was A up defined? The category A up. The Hom set X comma Y in A up was defined as A of all arrows in A up from X to Y are the same as all arrows in A from
A up to
all arrows in A up from X to Y are the same. How do you construct the opposite category? You just flip the arrows, right?
yes.
So A of X comma Y should be equal to, if,
X comma Y.
if this is an arrow in A op, what should the corresponding arrow in A be? I mean, what direction should it have?
The opposite direction.
So how do you write it? So if F op is an arrow here, F should be in which direction? In A. From?
From X to Y.
F op is from X to Y. So what should F, what should the direction of F be?
Y to X.
Exactly, Y to X. It's pretty simple, right? This is how you construct the opposite category, right? Don't confuse between these two notations. This let's use a different notation, S op, S hat for the time being. If you are confused, S hat is a functor. Forget that. I'm just talking about the opposite of a category. So given a category A, you can construct its opposite category, A op. The objects of A op are the same as the objects of A, but the arrows of A op are the arrows of A reversed in the written in the reverse direction. So if corresponding to every arrow F from Y to X in A, you should have an arrow F of from X to Y in A op. That is the idea, right? So what can I write this to entire set as? So A op of XY should be A of
A comma FB or something.
no. Forget B right now. Forget the functors. I'm just talking about the opposite category of a category. A and A op. We know that the arrows in A op are obtained by flipping the arrows of A. So you have this Hom set in A. You have this Hom set in A op from X to Y. What should the corresponding Hom set? What should the definition of this Hom set be? In terms of the Hom set of A, this should correspond to some Hom set in A. What Hom set should it be? A of X comma Y should be equal to A of
F comma G or something.
that is what I am stressing. Forget for the time being that there is something called F, G, etc. You have a category A. You have a category A op. We construct this category A op. It has the same objects as A. How are the arrows of A op written? So I should define this Hom set A op from Y to X, rather X to Y. As how do I define it? I should write it in terms of a Hom set of A. What Hom set of A is this?
Y comma X.
Exactly. That is what I was trying to. So A is your category, let's say, which looks like this. Then your category A op should look like this. You just keep the same objects, just flip all the arrows. That's all. So let's say there is one more arrow here. So in other words, if let's say this is object A, this is object A prime, this is object A, this is object A prime. So the hom set in A op from A prime to A is exactly the hom set in A from A to A prime, isn't it? You're just doing nothing, you're just flipping the direction of all arrows. That's all that you are doing. Okay, so what can I write this as? So what can I write this hom set as? A of GB comma A, what can I write this as?
Same thing, GB comma A.
No, in terms of A, how can I write this? So the hom set in A of from GB to A is exactly the hom set in A from
A to GB.
Exactly. That is the definition of the hom set in A op, right? By the way, for those who join right now, this is our problem. We are given an adjunction between two functors f and g in where f is the left adjoint, g is the right adjoint. What we want is to show that there is an adjunction between the functors f op and g op, where I hope that you remember the functors f op and g op. If you have an issue with this, you can write f hat g hat. Write some other notation. Don't confuse it with opposite category. I mean the way we write arrows in opposite categories. You can write this functor as f hat. You can write the functor g op as g hat. Okay. The point is that these two are functors, and what we want is an adjunction between these two functors, where now f op is the right adjoint and g op is the left adjoint. So accordingly, we have this data. There is an adjunction between the functors f and g. What we want is an adjunction between the two functors f op and g op. F op should now be the right adjoint and g op should be the left adjoint. So to show that there is an adjunction, we need to show that for every object A in A op and for every object B in B op, we have a bijection like this, which is natural in both variables. We are not focusing on the naturality part right now. We just want to show that there is a bijection at the level of hom sets. So what I want to show is that there is a bijection from this set, this hom set, to this hom set. So the idea is now to write this hom set first. Okay. So what we did was pretty simple. I just recalled the definition of how you write this functor s op or s hat. Okay. So it's pretty simple. We have seen this previously. If s is a functor from C to D, we can construct a new functor s op. Keep in mind that this is a functor. It has nothing to do with the opposite category notation, formalism, etc. It's just a functor. Think of it just like a notation or something. Okay. Don't confuse it with how you write an arrow of the opposite category as let's say f op or g op. If f is an arrow from something to something in a category A, you write the corresponding arrow in the opposite category by f op in the opposite direction. That op notation and this op notation have nothing to do with each other. Okay, this is a completely separate notation. You can, that is why I am stressing that you can also write, instead of s op, you can also write s hat. The important thing here is that this should be a functor. Okay, so s op is a functor from the opposite category C op to the opposite category D op. What does it do? Sends an object C here to an object of D op, which is the object SC. Keep in mind that the objects of the opposite category are always kept to be the same. So if S was a functor from C to D, so we know for that object C in C we have an object SC in D. What I am doing for S op is sending C to SC itself. So in other words, by definition, S op applied on the object C is just the functor S applied on the object C. And what does it do to an arrow f op? If f op is an arrow in your category C op, right, which means by definition of opposite categories, this f op should correspond to an arrow in C in the opposite direction. So it should correspond to an arrow f from C prime to C in the opposite direction, right? S was a functor from C to D. I can apply S on this to get an arrow SF from SC prime to SC in D. But what I really want is an arrow in D op. So what I'll do is I just look at the corresponding arrow SF op, which is from SC to SC prime in D op. And S op maps F op exactly to this arrow SF op. Okay. So what I really want to stress to you is don't get confused between this op used here and this op used here. This op is applicable only to arrows of a category, and it just is about formally flipping the arrows, right? Given an arrow F in a category C, you you write the corresponding arrow in the opposite category C op as F op. This op is a different notation, refers to this two used here, and this op here is a completely different thing. It's, think of it as a different notation. You can think of this as S hat. In fact, the idea is to get a functor from C op to D op, given a functor from C to D itself. This is a functor in itself, okay? S op is a functor. That is why this question also makes sense. Yeah, so what I do is I want this bijection, I'm sorry, I want this bijection from the left home set to the right home set. What I do is I look at the left home set. G op of B by definition is just GB, so this is just A op of GB comma A. Now how was the opposite category A op defined? Just keep the same objects as A, just flip all the arrows of A. That is how you get the category A op, the opposite category. So A op, the home set in A op from the object GB to the object A should exactly be equal to the home set in A from the object A to the object GB. Now keep in mind what, or recall what you had previously. You had two functors F and G, and you had an adjunction between them where F is the left adjoint and G is the right adjoint, right? So what I can write this is, since G is the right adjoint and F is the left adjoint, for the functors F and G, you had this previously. So I can write it as B of, so G comes to the left in the form of A, so Fa comma B, right? You can switch. That is the idea of an adjunction. You can take, I mean, if there is a functor applied on the left side, you can actually go to something which if a functor is being applied on the left side, you can actually switch to the right side by using another functor. That is the idea of an adjunction. And for people who have also studied operator theory, maybe probably, or even just linear algebra, you know that there are operators. I mean, for a matrix T, there is something called a matrix T star, right? Which sort of does exactly the same thing, except that for linear algebra, you can switch you can flip the inner product itself, in the sense that if you take inner product of Tx comma y, I mean, the definition of T star is inner product of the matrix T times x comma y is inner product of x comma T star y, right? I'm not getting into what exactly T and T star really are, what x and y are, but the formalism is this. This is the inspiration behind the name of an adjunction. Daniel Kahn was the one to come up with this, come up with the notion of an adjunction in category theory. And this was his inspiration, right? Inner product of Tx comma y is inner product of x comma T star y. That is why T and T star are said to be adjoint to each other. Except that in linear algebra, you don't have qualifiers like left or right, because you can write Tx comma, the inner product of Tx comma y is the inner product of y comma Tx. Inner product is symmetric, which is not the case with home sets, right, in category theory. That is why you have qualifiers like left and right in category theory. So in category theory, B of Fa comma B, this home set, all the arrows from Fa to B are, of course, I mean, this set is of course very different than than this home set, B of B comma Fa. These are different arrows. These are different arrows. There is no connection between them. These are completely different sets. Okay. For example, just look at the category of sets. Take a 6 element set and take a 1 element set. There is exactly one arrow from 6 to 1 in this category. While if you look at, if you look at arrows from 1 to 6, there is only one element. There are 6 elements here. There are exactly 6 arrows, right? So in set 1 comma 6 is completely different than set 6 comma 1. The point of saying all this is that home sets are not symmetric. You don't have this speciality in category theory, right? That is why you cannot flip. You cannot flip home sets, and that is why you have qualifiers like left or right adjoint in category theory, which you didn't have in analysis or linear algebra. So if B of Fa comma B should be the same as A of A comma GB, right? If being applied on the left of the comma is called the left adjoint of the adjunction, G being applied on the right of the comma is called the right adjoint of the adjunction. Okay, so A of A comma GB, which can be written as B of FA comma B, because F and G were part of an adjunction, with F being the left adjoint and G being the right adjoint. Now what I can write is, this is B of F of A comma B, right? This I can write because F of applied on A is exactly the object FA. That is how we define this functor, right? S hat or S op. And what is this? I just want to bring B op into the picture, the opposite category of B into the picture. So I can write this as B, not isomorphic, let's say equal to. It really doesn't matter here. So this is equal to B op of B comma F op A. Now notice that this is exactly what we wanted. We started with this, we arrived at this, which shows that now G op, I mean there is an adjunction between G op and F op, but now G op the functor G op is the left adjoint and the functor F op is the right adjoint. Okay, and you can check that because this bijection, because you had this bijection naturally in the variable A in A and B in B, you can check that this bijection that we have obtained right now by composing a sequence of bijections. I mean, from this to this you have a bijection, from this to this you have a bijection, from this to this you have a bijection, from this to this we have a bijection, or the identity if you prefer. This bijection that we have obtained is itself also natural in both variables A and B. So I'll just mention saying that check the naturality of the bijection in the variable A in A, or rather A op I should say, and the variable B in, variable B in B op. Okay, and that basically says that if there is an adjunction between F op and G op, with F op being the left adjoint of the adjunction, G op being the right adjoint of the adjunction. Sorry, I'm sorry, you had an adjunction between two functors F and G, where F is the left adjoint, G is the right adjoint. Now you produce new functors, F op, which is a new functor, G op, which is another functor, another new functor, and you produce an adjunction, or we have shown that there is an adjunction between these two functors, where now F op is the right adjoint, and I mean this new functor F op is the right adjoint, and this new functor G op is the left adjoint. Okay, yeah, that sort of settles the first part of the problem. Next thing is to show that right adjoints preserve terminal objects. So how do you show this? It's pretty simple. Forget that we were doing all these things so far. Just start with an adjunction between two functors F and G, where we'll denote where F denotes the left adjoint and where G denotes the right adjoint of the adjunction. Show that this right adjoint should preserve terminal objects. We know what preservation of limits is. In the case of terminal objects which are particular limits, this definition becomes even more simpler. So let's write it first of all, then let's come to this. So next part, start with, okay, you take an adjunction, you take functors F A to B and take a functor G B to A, and take an adjunction between these two, where F is the left adjoint and G is the right adjoint. We want to show that G preserves terminal objects. That is what we want to show. Right adjoints preserve limits. I mean, that's true in general, but we want to show that right adjoints preserve terminal objects. So in other words, want to show is this, that if 1 in B is a terminal object, then its image under G, which is G1 in A, should be a terminal object. So how do you show this? How do you show this? It's just a one line argument. How do you show this? Someone quickly tell me, Shrutin maybe. You start with a terminal object 1 in B, want to show that G of 1 should be a terminal object in A. What does an object being a terminal object mean?
So in B, the Hom set FA to 1 would be a singleton. Then under the adjunction A to in A would be A comma G of 1 would be a singleton.
Yeah, exactly. So the idea is, what is a terminal object? An object 1 in a category is called a terminal object. If given any arbitrary object in the category, there is a unique arrow from the arbitrary object to your terminal object. That is the definition of a terminal object. So 1 in B is terminal implies what? Terminal, or 1 is a terminal object in B implies that for all objects A in your category, for all objects B prime in your category B, right? This Hom set in the direction from B prime to B is a singleton. Let's write it like this, star. Okay, which implies in particular that for all objects A in B, right, this Hom set from FA to, I'm very sorry, I don't know why I'm writing like this. So 1 in B is terminal if for all objects B in B. I don't need a B prime here, I haven't used B even as a variable. For objects B in B, B of B comma 1 is singleton, which implies in particular for all objects A in B, A in A, this Hom set FA. So if A is an object in A, F is a functor from A to B, so FA will have to be an object in B. So B of FA comma 1 is a singleton, right? This is true in particular, which implies that for all objects A in A. Now we are using the fact that F is left adjoint to G to replace this B of FA comma 1 by the set A of A comma G of 1. I can carry, as I said, the idea of an adjunction is to switch, to carry a functor to the other side in the form of another functor. Okay, so I can write this as A of A comma G1, right? Right, so yeah, this is just isomorphic we know this FA comma 1. This is information that we have from the fact that F is left, since there is an adjunction, since F is left adjoint to G. So there is an bijection which is natural in A, and there's no point in saying one is fixed. Yeah, so there is a bijection in particular. So I can write this. So A of A comma G1 is isomorphic to as a set to B of FA comma 1. Now B of FA comma 1 is a singleton set, and isomorphism of sets is exactly about it's a property of cardinality of sets, right? Two sets are isomorphic implies in particular you sort of decategorify and you sort of say that these two sets will have the same cardinality. So if the second set B of FA comma 1 is a singleton, A of A comma G1 has to be a singleton. So notice what the last statement actually says. It says that for all objects A in A, the Hom set in the category A from A to G1 is a singleton, which means that given any arbitrary object A in A, there is exactly one arrow from A to G1, which implies that G1 is terminal.
Sir, what is that symbol inside the singleton set?
some star, some random symbol, doesn't matter. Just want to denote that it's a singleton. It doesn't really matter what you write. I mean, this is the point of category theory again, right? You are not interested in the internal structure of some object. You don't know if it has some internal, if an object has some internal structure or not. You only talk about things up to isomorphism. So this singleton star is the same as this dot, let's say, is the same. For a category theory, is these two objects, this object, that is this set, and this set are equal, are the same. Yeah, so the point is we have shown that G1 is terminal. So G was a right adjoint, and we have shown that G right adjoints preserve terminal objects, which is exactly what we wanted. In the next week, I'm pretty sure you haven't seen it in this week, but in the next week you will in fact see something more stronger, that right adjoints have this amazing property that they preserve limits. So dually, left adjoints preserve colimits. Yeah, so I've already answered our last question, which asks that what does a duality principle tell you? Okay, so the reason behind these two seemingly disjoint problems was to get to the final problem. So first the first problem was to show that there is an adjunction between f op and g op, where f op is the right adjoint and g op is the left adjoint, which sort of, in a sense, sort of says that the notion of a left adjoint and the notion of a right adjoint are dual to each other. So if f from A to B is the left adjoint of some adjunction, then f op from A op to B op is actually the right adjoint of some adjunction. So left adjoints and right adjoints are dual notions of each other. And the second thing that we proved was that right adjoints preserve terminal objects. So what can we say about using the duality principle? What does the exact dual of this statement what should the exact dual of this statement be? If right adjoints preserve terminal objects, what should left adjoints do? Yeah, what should the dual statement be?
Left adjoint preserve initial object.
Exactly, and in fact we can check this. So dual statement left adjoints preserve initial objects. And how do you see this? The idea is very simple, using the duality principle. So proof is pretty simple. Suppose that you take A, B, f is a functor from A to B, G is a functor from B to A, and assume that there is an adjunction between these two functors f and G, where f is the left adjoint of the adjunction and G is the right adjoint of the adjunction. We want to show that f preserves initial objects, right? The left adjoint preserves initial objects. So let 0 in A denote an initial object. By the way, 0, 1 are just abstract symbols. Or B an initial object, not denote. B an initial object. A category might not have an initial object. So B an initial object.
So is that 0 belonging to A or O belonging to A?
It doesn't matter. 0, A is the same thing. It's just a notation. I can write I as well. Here I am talking about, I am using the notation 0. So let 0 in A be an initial object. I want to show that f of 0 in B is an initial object. This is what exactly means for a functor to preserve initial objects. Right? I want to show this. So I can use a similar argument as before, like this one, this chain of isomorphisms that we have to obtain this, or we can just use the duality principle. So how exactly? So note that we have proved that if f is left adjoint to G, then the functor f op from A op to B op will be right adjoint to the functor G op from B op to A op. Right? Exactly. What have we seen? We know we have proved that right adjoints preserve terminal objects, and since 0 is an initial object in A. What is 0 in A op? It's exactly a terminal object, because limits and co-limits are dual to each other, which means in particular initial objects and terminal objects are dual notions of each other. 0 is a terminal object in A op, right? Now f op is a right adjoint functor whose direction is from A op to B op. So because we have already proved this, that right adjoints preserve limits, so f op of 0 is a terminal object. In B op, right? And f op of 0 is just f of 0 by our very definition of the functor f op, which implies that f of 0 is an initial object in B, which is exactly what we wanted. Okay. So left adjoints preserve initial objects, right adjoints preserve terminal objects. So if you see some functor which fails to preserve, let's say, terminal objects, you can understand that it can never have a left adjoint, because if some functor has a left adjoint, which means that the functor itself is a right adjoint, then it should preserve terminal objects. So we can just use the contrapositivity of this result, right, to show that some functor fails to have a left adjoint. You can just show that the functor itself fails to preserve terminal objects. So for example, the free group functor from sets to groups, I'm sure you have seen the definition, such an example this week. Fails to, you know already that this free functor from groups, from sets to groups, is a left adjoint of some adjunction. The right adjoint is a forgetful functor from group to set, right? So you know that this is a left adjoint. How do you guarantee that this is not a, how do you guarantee that this itself doesn't have a left adjoint? So you know that free is left adjoint to forgetful. How do you guarantee that there is not another adjunction in which free is the right adjoint to some functor? Okay. The idea is, observe that this free functor fails to preserve terminal objects. Why? Because what is a terminal object in set? It's just singleton, right? And free functor maps it to the free group generated on a singleton set, which is Z, which fails to be the terminal object of group. The terminal object of group is the trivial group, right? So the free functor doesn't preserve terminal objects, right? Which means that the free functor cannot have left adjoint. Okay. Okay, that finishes the first problem. We spent almost an hour on the first one. Let's get to the second one. Okay, let's try to solve the second one, then we'll come to other ones. So as discussed previously, we have also defined the notion of a functor creating limits or creating co-limits. So what is exactly the notion of creating a limit? So suppose you take a functor from a category A to a category B. I'll say that the functor f creates limits if starting with any diagram in your domain category, right? If you look at the image diagram and consider any limit cone on the image diagram, then there should exist a cone on the original diagram in the domain category whose image under the functor should be isomorphic to that limit cone in the codomain on the image diagram in the codomain category. Okay, that is what creating limits means. So we want to show that the forgetful functor u from group to set creates limits, and this sort of is related to one of the exercises we had in the previous week, which I asked you to solve, which is this one, that how exactly do limits in set look like? Give an explicit description of the limit of some diagram D in set. So let's just quickly solve this first, and then we are almost done. So we want to show that u from group to set creates limits. So take a diagram D from some category J, some small category J into group. The definition of, I mean, the to show that this functor creates limits, what you want to show is that you look at the image diagram, right, which is U compose D, and you take any limit cone on the image diagram. You should have a limit cone on the original diagram whose image under the functor is isomorphic to that limit cone in the image diagram, right? So take any limit cone, let's say take any limit cone, okay, let's do it like this. Okay, so we should start with an arbitrary limit cone on the diagram, on the image diagram, right? And then show that there is some cone, or rather in fact limit cone on the original diagram whose image under the functor is isomorphic to that limit cone. So let's just quickly understand how exactly do limits in sets look like. Okay, so consider the diagram. Consider the diagram U compose D from J to set. Set itself is a complete category, right? Which means that all diagrams in set have limits. So U compose D in particular should have a limit. What exactly should this limit be? So let's quickly try to figure this out. So this is our first aim. Okay, rather independent aim. So how should I say this? Okay, let's in fact solve the problem here. Then we are done. Yeah. For the time being, just focus on this problem. You start with a diagram D in set of shape I. We want an explicit description of the limit of D, right? So want an explicit description of this limit I D. Okay. So this is a set, right? This is an object in set, so it has to be a set, right? And how exactly do we access the elements of a set? So what is exactly an element of a set A? It's just a map from a singleton set to that set, right? This is exactly the idea. So the set of all maps from singleton to A is exactly the set A, right? Given any map from singleton to A, you just look at the image of the unique element of the domain under the map. That gives you an element of A. Conversely, given an element A in A, you do have a map from singleton to A, which sends the unique element to A. So there is a bijection, right? So note that if, let's denote the singleton by 1 right now. If 1 in set denotes the singleton set, then set of 1 comma some set A is exactly the same, isomorphic to the set A, right? So to understand this set, it is enough to look at maps from 1 into this set. So limit ID is isomorphic to the set of all maps in set from 1 to this. Now we use a universal property of limits. The universal property of limits exactly says that this is the same as the set of cones on the diagram D with vertex 1, right? That is all natural transformations from delta 1 to D. A cone on D is exactly a natural with vertex 1 is exactly a natural transformation from delta 1 to D. And every such cone factors uniquely through the limit cone, in the sense that you should get a unique map from 1 to the limit object, which makes everything commute, right? So this is just the universal property of limits. If you are not convinced, just have a look at the picture, or maybe okay, let me just draw something. So the idea is D is a diagram. This is, let's say, the limit cone, limit ID, right? Take any arbitrary cone on this diagram with vertex 1, right? The universal property of limits says exactly that this arbitrary cone should factor uniquely through the limit cone, in the sense that you should have a unique arrow from 1 to limit D which makes all small triangles commute. So the idea is, whenever you take a limit cone, whenever you take an arbitrary cone, you get an arrow from the vertex of that cone to the limit, right? Conversely, if you take an arrow from some object to the limit, you can compose all these arrows together. So this arrow composed with this gives you some arrow, this arrow composed with this gives you another arrow, and so on. So the idea is that the set of maps from an object to the limit is exactly the set of cones on the diagram T. Okay, every arbitrary cone factors uniquely through the limit cone, and conversely, if you have a map from an object to the limit, then you already have, just by composing arrows, you have a cone with that object being the vertex on the diagram D. So these two are the same. Now what is this set? Cone delta 1 comma D. This is exactly the set of natural transformations from the constant functor delta 1 to the functor D, right? What is this? This is exactly I'm sorry, this is exactly the set of so what is a natural transformation from delta 1 to D? A natural transformation delta 1 to D is a family, right? That's all it is.
Sir, here delta is a triangle, right?
Delta 1 is the I hope that you are seeing the lectures, by the way. Delta 1 is just the constant functor. So delta 1 is a functor from J to set, which sends every object of J to the singleton set 1. Here 1, so delta of any object A of set is the constant functor which sends any object little j of J to A, to the constant set A, and sends any arrow to, so sends any arbitrary arrow from J to K to 1A, the constant functor on an object. That is what delta A is. So delta 1 here is exactly the constant functor on the object 1.
Yes, got it.
So it is a family of maps delta 1 applied on some object of J to Dj, with exactly one map for each object J in J, right? And what is this exactly? This is exactly a map, yeah, such that something should hold, is a family such that for all arrows, this is the definition of a natural transformation exactly, for all arrows u from, let's say, J to K in J, right? Yeah, let's call this alpha J. So alpha, a natural transformation, is exactly a family of alpha j's such that for all u from J to K in J, you should have this commutative diagram delta 1 J, which is exactly 1, right? From this to Dj you have alpha J, from this to Dk you have alpha K, from Dj to Dk you have D of u, right? This triangle should commute, right? Exactly this. So yeah, this is let's write this as an arrow from 1 to Dj, because delta 1 of J is just 1. So this family is exactly a family of arrows alpha J from 1 to Dj, J in J. Okay. So what does an arrow from 1 to Dj mean? We just explained that an arrow from a singleton set to any set is exactly an element of the codomain set. That's all it is, right? So alpha J, which is a map from 1 to Dj, is exactly an element of Dj, right? So you can think of alpha J as an element of Dj. And what does the commutativity of this triangle mean? So du is a map from Dj to Dk, right? Alpha J is an element of Dj, alpha K is an element of Dk, and the commutativity of diagram exactly means that du, this map du, takes the element alpha J to the element alpha K. That's all that it says, right? So let's write it here. So such that this holds, which is equivalent to saying that a natural transformation, or which is equivalent to which is equivalent to, I mean, a natural transformation alpha from delta 1 to d, which we have just explained here as a family such that this triangle commutes, is the same thing as a family of elements. This is your family xj in dj, right? J in j. So for every j in j, you pick one element xj, which you can think of alpha j here, from the set dj, such that this family should have this property that for all arrows u from j to k in j, du applied on the element xj is exactly the element xk. Okay, and now we are done. So we stopped here, right? The set of natural transformations from delta 1 to d, and we saw that a natural transformation alpha from delta 1 to d is exactly the same as a family of elements which satisfies this property. So I can write this set. So let's copy it here. Oops. Paste here, yeah. So what we have ultimately is, this is equal to or the same as families xj in the product of all dj's, d of j, j in j, right? So this means that xj, for each j in j, xj is an element of dj, such that for all arrows u from j to k in your category j, du of the element xj, so du will be a map from dj to dk. So xj is an element of dj, du can be applied on dj to obtain xk.
Sir, is
Yeah.
this the fourth problem of last week or the second problem of this week?
This is the first problem. This was the last problem of last week.
Okay, you're still continuing that.
Yeah, we just wanted to explain what limits look like in set. So this is exactly what the limit underlying set of the, or this is what the limit set of a diagram should look like in the category of sets. Okay, so in any category, if you take a diagram, the limit of that diagram should be an object in that category. So in particular, if we take the category of sets, and a limit of a diagram in the category of set should be a set, and this is exactly how this set looks like. Okay, in fact, you can also go on to talk about the projections from the limit. I mean you can in fact describe the limit cone, right? So from this to each dj you should have a map, and that map should, here in this case, should be just the projection map. You can check that this pi k, dk, and so on, you can check that this will indeed, and again you have pi I, let's say, for some di object. You can check that this will be the limit cone on this diagram d that you started with. Okay, but let's not focus right now on this, or maybe we should, because we need it for our problem. So in fact, check that limit j, we went from j to I mean I to j, yeah, j, capital J is supposed to be I. Limit I, where else did I write a j? This is I, this is I, this is I, the shape category is I, yeah. So in fact, check that with this description of your limit I d, together with your projection map. So di pi I, dj pi j. I'll like write down what pi is, dk pi k, and so on. So let's use a different color for this, or maybe let's write it like this. So in fact, check that this is a limit cone on the diagram D, where for each I in your category I, pi I from limit id into di is the projection. So what does an element look like? An element of the limit looks like a family, is exactly a family xi, right? I in I, that is what we proved. You map it to the element xi, you project it onto the ith component. This is your map. Okay, yeah, that's about it. This is how exactly limits look like in sets. Any diagram, you take any diagram D, its limit will exactly look like this. The set of families, I mean the set of the vertex of the limit, that is, that set should look like this. An element will exactly be a family xj of elements of dj, where j varies of course in I, such that for all arrows u from j to k in I, the function du applied on xj is exactly xk. Okay, so this is exactly how limits in the category of sets look like. Now what you are asked is, you want to show that the forgetful functor u from group to set creates limits. We come back to our original problem right now. We want to show that the forgetful functor u from group to set creates limits. So we start with an arbitrary diagram D from J to group, right? We want to show that for any limit cone on the image diagram U compose D, right, in the codomain category set, you should have a cone on the original diagram which is a limit cone and which gets mapped to onto that particular limit cone in the codomain, right? So take, again I am not using the slightly more complicated definition of creation of limits, because I believe things have already gotten a bit complicated today, and that is why I am trying to keep it simple. But yeah, you can also check the other, I mean the more general, the more inclusive notion of creation of limits. But let's, for the time being, let's focus on this definition. So take what exactly, yeah, take a limit cone. Take a limit cone, limit j of the diagram U compose D. This with the, keep in mind how exactly do limits in sets look like. U compose D is a diagram in set, right? This is U compose D. These are projections pi, 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 yeah. So take a limit cone on the diagram U compose D in set, in the category set. By our previous problem that we had or saw, what exactly this is, this cone? So first of all, let's explain the vertex again. The vertex, which in this case will be a set, is exactly families xj, j in the product of u of d of j's, right? J in j, right? The functor here is U compose D. UD is your functor. UD is your diagram in set. So that is why we have UD, right? Such that for all arrows U from J to K in J, DU applied on XJ is exactly D. I mean UDU applied on XJ is exactly XK. Yeah, probably a bit confusing, but U is your functor. Okay, capital UD, I mean U composed with D is your functor here. This is exactly how a limit in this exactly looks like. Okay. So what was D exactly? D was a diagram in group, right? So for each J in J, D of J was a group. What is U applied on DJ? It's the underlying set of the group DJ. That's all. So what I mean to say is, for all J in J, DJ is an object in group. So is a group, right? Is a group. So any element of your limit of U compose D is actually a family xj, J in J, of elements of UDJ, right? That is elements of the underlying set of DJ, where J varies, of course. Which means what I want to say is xj is in particular an element of DJ as well, right? And DJ was a group for each J. So what I'm trying to say is, just look at this particular set. Can we not produce a group structure on this set? That is all, after all, that is what we want, right? What we want is, we should have a limit cone on the original diagram D. So we should have a vertex object in particular. That object should be an object of group, right? So that should be a group. And that object is something which gets mapped by the forgetful functor to our limit, to this limit. What does the forgetful functor actually do? It just forgets the structure. The underlying set is the same, right? Which suggests that if we want a limit for the diagram D, its underlying set should be this. There should be a group structure, but the underlying set should be this, right? That is what roughly it says. So what we want essentially is a group structure on this set. So let's put a group structure. On the last set, let's say, or the above set. It's pretty simple. Each DJ is a group. We are just, so think of it in so think of it in this way. This is DJ, this is DJ prime, and so on, right? DJ is this group, DJ prime is this group, DK is this group, let's say, and so on. This is some J double prime, let's say, and so on. Think of these sticks as the elements of the group. So each element here is an element of the group DJ. Each element here is an element of the group DK, and so on. Okay. What is an element of the limit? It's exactly a family of xj's with exactly one element xj from each group DJ or each set DJ, right? So it's just a section of this bundle, roughly speaking. This is what a family xj is. Xj, J in J. I'm trying to be as pictorial as possible here. So think of this sticks all together like a bundle of sticks. Okay, you just make a cut. Okay, so through every J, through every index J, this is the index J, this is J prime, this is K, this is J double prime. Through every index J, you just choose one particular point, right, which is a particular element of the family xj. So xj is this element, xj prime is this element, k is this element, xj double prime is this element. Okay, a single family like this is an element of your limit, where you should have this extra property that for all arrows u from j to k in J, that family should satisfy this property, right? So how hard can it be to put a group structure on this set? The set is understood, right? Each element of the set is exactly this family. That is, pictorially speaking, each element of the set is just this section. That's all, right? We want to put a group structure. So so define a group structure. So xj, J in J, star, take some other element of the limit, let's say yj, J in J. Okay, these are two different elements of the limit. This is an element, okay, both are elements of limit J u compose D. Okay, the image diagram, we started with the limit cone of that diagram, right? The limit of that diagram exactly looks like this. We are trying to put a group structure on this. So this is how we put a group structure. So xj for each j in j, xj is an element of the group dj, right? It's an element of u compose dj, but u compose dj is just the underlying set of the group dj. So it's an element of the group dj, and yj is itself an element of the group dj. So both the xj and yj are in the group dj. So this we can write. This is xj dot yj, j in j, as for each j in j, xj comma yj are both elements of dj, which implies that xj comma yj, sorry, both are elements of u of d of j. U is just the forgetful functor, which implies that xj yj both belong to dj, and dj is a group. Right? So this is just this is the product. Check that star is a group structure, in fact. On your limit j u of d, I'm sorry, u compose d. Check that this is a group structure. Now think about what exactly have we achieved so far. Let's draw a diagram. So this is your group category, this is your category set. You have this forgetful functor u. You started with a diagram d in group, right? You looked at the image diagram u compose d, right? You had you started with a limit cone arbitrary on u compose d. We sort of came up with an expression of the limit of diagrams in sets. So we know that the limit here, limit j is the shape of the diagram. So limit j u compose d. We explained this set, we wrote down this set explicitly. Exactly this is how it looks. An element looks like a section, right? So we know what this set is. We put a group structure on this set, right? Which makes this as an object, which makes this an object of group, right? In fact, check that your group structure that we have on u compose d also makes the projection maps group homomorphism. So let's draw this diagram a bit later. In fact, also write this. In fact, check that this group structure makes each projection pi j from the limit j u compose d into dj, I mean u of d of j. So earlier we described what exactly a limit cone in sets looks like, right? A limit cone in set exactly looks like, where did I write it? Like this, where the limit set was described as set of families, and the arms of the cone are exactly projection maps, right? So I hope I have written it somewhere here. By a previous problem, let's point out that problem in week 4. Limits in sets exactly look like this, and check that each projection, in fact let's write the projection xj j in j maps to the element xj. You are projecting into the jth component. This might we could also write xi I in j maps to xj. I mean, just not, don't get confused. So each projection is a group homomorphism. From this group limit, I mean from, is a group homomorphism from this set applied, I mean endowed with your group structure star that we have. to the group dj. Okay, so the point of all this, saying all this or doing all this, is that these are projections, by the way, pi j prime, pi k, and so on. The point of doing all this is that we in fact have obtained a cone, at least limit j u compose d comma star, let's say we have obtained a cone. So limit j u compose d, which is a set together with your star, making it into a group together with your group homomorphisms given by the projections, right? So we have obtained a cone in group. Okay. So we have obtained a limit cone. In fact, we have obtained a cone on the diagram D in the category GRP. Okay. Interestingly, note that what does u do? U exactly maps this group, in fact this cone, to something which is isomorphic to this. Just for the sake of simplicity, here we have done it in this way, that it maps exactly to this cone. It's in a sense it strongly creates limits, but the idea is that this cone is getting mapped to something which is isomorphic to our chosen limit cone. Okay, right? And in fact, check that this cone that we have constructed in the category of groups on the diagram D is in fact a limit cone. This is exactly what construction of limits means. You start with any diagram in your domain category, look at the image diagram, take any arbitrary limit cone on the image diagram, take any limit cone on the image diagram. There should exist a cone on the original diagram which is a limit cone and which gets mapped to your chosen limit cone in the codomain category on the image diagram. So we did exactly this. We started with the diagram D, we looked at the image diagram, we started with an arbitrary, we started with a limit cone on the image diagram. We constructed, or we showed that there is indeed a cone on the original diagram which gets mapped onto that limit cone. And this cone, which you need to show yourself as an exercise, and very easy in fact, check that this check that this cone is a limit cone on the diagram D. So D is your diagram. We have constructed this cone, right? Limit j u compose D comma star together with the projection maps, right? Star was defined in such a way that in fact the projection maps also become group homomorphism. So this is entirely a cone in group, in the category of groups. Check that this cone that you have in the category of groups is indeed a limit cone, right? And this sort of proves that the forgetful functor U creates limits. And as a consequence, interestingly, since set is complete, since set has all limits, this actually proves that group also has all limits. Okay, I'll just write one more line for this. As a consequence, okay, maybe an observation. This is true for creation of limits in general, that since set is complete and we have a functor from group to set which creates limits. Here we don't really need that it should be a forgetful functor. That might not make sense for arbitrary categories. The point is that U should be some functor from group to set which creates limits. Hence GRP is itself complete. Because why exactly? What do you need to do to show that GRP is complete? Start with the diagram, show that it has a limit. We have exactly done exactly this thing, right? We started with the diagram, we assumed something, we started with the diagram, looked at the image diagram, considered a limit cone on the image diagram, right? But the point is, if you take this diagram D, just look at its image. Since set is complete, there has to be a limit cone on the image diagram. Since U creates limits, there is a cone on the original diagram which is a limit cone and which gets mapped mapped onto that cone, right? Forget all those things. The point is there. In fact, the idea is there exists a limit cone on the original diagram D, which is exactly what we wanted, right? So every diagram in the category of groups has a limit. Hence, group is complete, and the forgetful functor and the functor U from group to set preserves them. Preserves limits. This is like an observation or a bonus of something of a functor creating limits, right? In fact, you can also show something. In fact, you can also show that if a functor creates limits, it will also reflect limits as well. So again, reflection is a property of. Reflection deals with property of a cone being a limit, and creation is actually creating a cone, which is a limit cone. This is the subtle difference between these two things. But creation is a stronger notion. You can show that if a functor creates limits, it will reflect limits as well. Yeah, I hope that the pictures were at least clear here. Sort of made the thing clear. If it's not clear, just do send me a message or an email sometime. Okay, let me ask you, Srisha, is everything okay right now?
Yes, sir.
Okay, I hope that it was. Probably the writing so much made it a bit of heavy, I guess. But I hope the ideas are clear, right?
Yeah.
The point is that the forgetful functor U from group to set creates limits. This is the idea. And please do try to have a look at the lectures before you come to the sessions. It's sort of understood that you didn't take a good look at the lectures, which is why the notations seem to be a bit difficult for you right now. But please do have a good look at the lectures. Otherwise, it will be very difficult to explain stuff.
Yes, sir.
Okay, let's see. Let's solve one more problem. I'll keep 3 as an exercise maybe. Let me just think which one is simpler right now. Okay, I guess we should keep 3 as an exercise, or rather as a practice problem. In fact, next week you'll learn something called the adjoint functor theorems, right? And this is sort of just a special case for the adjoint functor theorems. This is just easier to prove, that's all. It deals with posets considered as categories. So posets are exactly thin skeletal categories, which is what makes proving this simple. But in general, there are adjoint functor theorems which give you conditions under which a given functor has a left adjoint or has a right adjoint. So that is more general, but my point being behind saying all this is that you will see something like this in the next week, from which this will follow like a corollary. Okay, so that is why I'll leave this as a practice problem. We'll solve the last one and then stop. Okay. So let's quickly go through the problem. Suppose C is a small category and A is an object in C. Okay. So C is a small category, A is an object in C. We can consider the functor category C op comma set, whose objects are exactly the functors from C op to set, and whose arrows are exactly the natural transformations of functors, right? So this functor category is also sometimes called the category of presheaves on the category C. Okay, a functor from C op to set is exactly what is called a presheaf of sets on C. Anyways, so this is your functor category. We have seen this functor category previously as well. If you recall, in the lectures on representables, you saw this Yoneda functor, right? Yoneda embedding functor, which is a functor from C to C op comma set, which sends every object A to the corresponding representable functor C of gap comma A, right? And the interesting thing about this functor Y is that this functor is fully faithful, right? It's full, by which I mean it's locally surjective, as well as faithful, by which I mean it is locally injective. So it is locally bijective. So you had a fully faithful. So y is a fully faithful functor from C to C of comma set, and hence y is like an embedding of C into its presheaf category. So you take a category C. Suppose this is your presheaf category. So this is C. This is C of comma set. What y does essentially is embed C as a full subcategory of C of comma set. That's what it does, right? In fact, y has a particular universal property itself, or rather I should say that y together with this has a universal property, in the sense that this category is like a free co-completion of the category C. Okay, too many terms, forget that, but point is that this category is in fact itself special. In fact, you learned something about functor categories this week, that limits and co-limits in functor categories are computed object wise. Using that, since set is complete, you can in fact show that this category itself has all limits and co-limits. So in particular it has all co-limits, so it is co-complete in particular, and the universal property of free co-completion deals with that. But yeah, anyways, we have seen this previously, this functor y previously, and this functor category C of comma set previously. So let's quickly look at the problem. So you consider this functor category C of comma set and consider two objects f and g in C of comma set. Okay, so f is a functor from C of 2 set, g is a functor from C of 2 set, right? What they are asking you to show is this, that if so C of comma set, keep in mind, is a functor category. It has coproducts, right? Because set has coproducts in any functor category will be computed object wise if they exist. So since set has coproducts, the coproduct of the two functors f and g in the functor category will also exist, right? So take f and g in your functor category. If the coproduct of f and g is actually a representable functor, what the problem is asking you to show is that either f or g must be the constant functor with value empty set. Okay, so want to show this, that if coproduct g is a representable functor. Okay, so let's quickly recall what the coproduct is. I'm pretty sure if we don't, we'll be in trouble. So let's quickly recall. Please do have a look at the lectures. So if coproduct G is again a functor from C of 2 set, what does it do exactly? Limits and co-limits in functor categories are computed object wise. So the coproducts in functor categories in particular be computed object wise, and it should map an object A to this set FA coproduct GA. It maps an object B to FB coproduct GB. It maps an arrow F from A to B to this arrow FF coproduct GF, where this arrow is exactly induced by the universal property of the coproducts involved. Okay, so what is this arrow exactly? Since we are in the category of sets, we could describe this arrow using the universal property, but since we are in the category of sets, just to make things simpler, let's try to describe this set theoretically. What does this map do? Sends any object. So what is this coproduct? What is the description of a coproduct of two sets? This is just the disjoint union, right, of FA and GA. So what does it do? It sends some element X in FA onto the element FFX in FB. What does it do? What does this map FF coproduct GF do? It sends some element, it sends any element X in FA to the element FFX in FB, and sends an element Y in GA to the element GFY in FB. Right? It's pretty simple. This is the description. Okay, this is your FA, this is your GA. FA coproduct G is exactly looks like this disjoint union of these two sets. That's all, right? And what does this map FF coproduct GF do? This is a map into the disjoint union FB GB. What does this do? You take an element X here, X is getting mapped onto FFX. Okay, so let's write it like this. And what does it do to an element Y on the other hand? An element Y in GA gets mapped onto the element GFY under this map. This is the description of the map. That's all. Okay, this is your functor. You can check, in fact, this is a functor. No need to check because this week sort of covered this fact. Limits and co-limits in functor categories are computed object wise. So in particular, F coproduct G will be a functor defined in this way, will in fact be a functor. Yeah, so what does the problem now ask? So want to show the following, that if coproduct G is representable, then either F is the constant functor on the empty set or G is the constant functor on the empty set. What does the constant functor again do? We have seen this in previously in the definition of limits and co-limits. So the constant functor on any object sends every object to that object and sends every arrow to the identity arrow on that object. So in particular, for the empty set, the constant functor from C up to set, so where sends every object C to the empty set, sends any object C prime to the empty set, sends any arrow F to the identity arrow on the empty set. Okay, that's all that it is, identity map on the empty set. That's all that this constant functor on phi on sorry, not phi, the empty set should be pronounced as OE. Okay, it's a Danish letter, it's not a Greek letter. Yeah, that's all that delta OE does. So we want to show that if the coproduct of F and G is representable, then either F is the constant functor on the empty set or G is the constant functor on the empty set. That's all that we want to show. So it's like a very interesting connectedness property of representables. Okay, so did you study topology previously?
Nope.
Okay, so let's not mention. Yeah, so let's this is pretty simple. Let's do this. So assume that F coproduct G is C gap comma A for some object A in C. We want to show that either F is a constant functor on the empty set or G is a constant functor on the empty set. So question is, how exactly do we do this? How exactly do we do this? What do you think? I'm sorry, I shouldn't write equal to, I should write isomorphic to. So naturally isomorphic to. Yeah, continue.
What was the question?
The question is, we want to show that given this assumption that if F coproduct G is naturally isomorphic as a functor to some representable functor C gap comma A on C, we want to show that either F is the constant functor on the empty set or G is the constant functor on the empty set. So it's like as if F does nothing or G does nothing, something like that, because the constant functor on empty set coproduct any functor G will exactly be isomorphic to G, naturally isomorphic to G. Okay, so it's like it's the same as showing that F is isomorphic to the representable functor C gap comma A or G is isomorphic to the representable functor gap comma A. This is the question. Yeah, so how do we show this? So let's try. So since we are given a natural isomorphism, let's fix a natural isomorphism. So let alpha, let's say, from F coproduct G to C gap comma A be a natural isomorphism. Okay, suppose this is a natural isomorphism. So, or in fact, let's see which way is better. Okay, this way is better. Uh, so in particular, alpha, if you look at the component of alpha at the object A, alpha A from F coproduct G applied on A, which we already know is just Fa coproduct Ga to C A comma A is an isomorphism of sets. That is a bijection because these are sets. Right? Now C1 A comma A has a particular distinguished element. What is that? The identity arrow on the object A, right? So it has 1A in particular, right? So if we use this bijection and look at the element in the domain which gets mapped onto 1A, because this is a bijection, there will exist a unique element in the domain. So consider the element alpha A inverse of 1A. This is an element in the domain Fa coproduct Ga. Fa and Ga are disjoint, which means that this element will belong to exactly one of these two, right? So suppose alpha A inverse of 1A is in Fa. So note that what does this mean? This means that if at A, this set, if applied on A, this set is non-empty because we have assumed that there is some element in this set, so it is non-empty, which means that F cannot be the constant functor on the empty set anymore, right? So to conclude the problem, we have to show that G is the constant functor on the empty set, right? So G of any B should be empty. That is all that we want to show. Since by assumption Fa is non-empty, right? So we claim that G is the constant functor on the empty set. So G of any B will be empty. That is what we claim. Note that to show that G is a constant functor on the empty set, it is enough to show that G applied on any object is the empty set, because any arrow should get mapped to some arrow from any arrow in the any arrow, how should I say this? Yeah, any arrow in the domain of G should get mapped to some arrow from empty set to empty set, and there is exactly one arrow from empty to set to empty set, which is the identity arrow, because empty set in particular is an initial object, by the way, in the category of sets. Yeah, I wrote something wrong here, which is this. So the direction should be properly written. You take an arrow f op from A to B, because C op is your domain category. You should get an arrow ff coproduct GF, or rather f op coproduct GF op, whichever suits you. But the idea is the image arrow should be in the opposite direction. I'm sorry. Yeah, this is correct. There's nothing wrong. F op is an arrow from A to B in C op. So F is an arrow B to A in C, right? Which implies FF is an arrow FB to FF is an arrow FA to FB, because F is a contravariant functor, G is a contravariant functor. Yeah. Oof. Yeah, this is correct. There's nothing wrong in this. What else did I write? Yeah, it's okay. So we claim that G is this. Okay, G is empty. So note that, and I'll write this a bit cryptically. Note that, or rather, let's write it properly. Since there exists a unique arrow empty set to empty set, which is the identity. It is enough to show that G of B is the empty set for all B in the category C op. Okay, in the domain category C op. Okay, so assume G of B is non-empty. Assume that this is non-empty. We have this natural isomorphism alpha. We can look at its component at the object B. So alpha at B, which is a bijection of sets from FB coproduct GB, disjoint union GB to CB comma A, right? We are almost done. CB comma A, right? This is a bijection. So assume GB is non-empty, which implies what? Yeah, I don't think we don't need the bijection here. Yeah, we just need a fact that we have a map. Since alpha at B is a map, this to this, since the domain has been assumed to be non-empty, this implies that the codomain CB comma A is non-empty. Okay, which means, yeah, so the idea is you can never have a map from a non-empty set to an empty set, right? So if you have a map from some set to some set, and if the domain is non-empty, the codomain has to be non-empty, right? So GB is non-empty implies the domain FB coproduct GB of this map is non-empty. So since alpha B is a map from FB coproduct GB into CB comma A, CB comma A is non-empty. So there exists some map F from B to A in C, right? And now we are almost done. Since alpha from F coproduct G to C, yeah.
Can I scroll up just a minute?
Yeah. Do you have a question? Okay.
I think I missed the last line.
Sorry?
I missed the last line. So
Okay.
there exists.
Yeah, there is an arrow F from B to A and C. By the way, these notes are always available to you guys, right? You can see them.
Yeah, there is the drive link.
Yeah, and also there's the YouTube link of these lectures, right?
Yes, it's all there in the spreadsheet.
Yeah, okay. Just wanted to confirm. Yeah, since alpha from F coproduct G to C gap comma A is a natural isomorphism, and in particular a natural transformation, or let's write it like this. I mean, because we are focusing on the components right now, it's exactly the same. So since alpha at C, let's say, where C is a arbitrary variable, to C comma A, it was a bijection and it is natural also, is natural in the variable C. So we can use the naturality for the arrow, or look at the naturality square generated by this arrow F op, right? So for the arrow F op in your domain category A to B, domain category is C op, right? So F was an arrow from B to A. So for this F of A to B in C op, we should have a commutative square. We have a commutative square. What exactly is this square? This is so if A coproduct GA, C A comma A, right? If B coproduct GB, C B comma A, right? You have alpha at A, you have alpha at B, right? F op is an arrow A to B in C op. So this is FF coproduct GF. And what is this? So this is just so A to A you have an arrow, and yeah, so B to A you, so F is from B to A in C and A to A. So gap composed F, I believe. This is your, yeah, exactly. This is your map. So this map gap composed with F sends any G to G composed F, right? Because yeah, so from B to A and then you apply G. Yeah, so this square commutes. This is what we know. So in particular, if we start with our element alpha A inverse of 1A, which is in FA, right? That is what we had, right? This element. So this element was in the disjoint union. We assume that this element suppose belongs to FA. So this element is in entirely in FA. If you apply alpha A, you arrive at the element 1A. Upon taking the map or applying the map bar composed with F on 1A, you get the map F just. And upon applying this map on the element alpha A inverse 1A, which is an element of FA, you should arrive at an element FF of alpha A inverse of 1A, which is in FB, right? Because that is how exactly this coproduct map was defined. It takes elements of FA onto elements of FB, takes elements of GA onto elements of GB. It keeps in mind the separation between FA and GA, right? It keeps in mind the coproduct. So since this since this is an element of FA only, its image under this map FF coproduct GF should be an element of FB only, right? Yeah, so now we are done. So since GB is not, since alpha B is a map, so we do need it's a bijection. Since alpha B is a bijection, oops, I don't know why I cannot write here. Yeah, since alpha B is a bijection from FB coproduct GB to CB comma A, what we do is we take some arrow F in C which comes from GB. Okay, so take an arrow, since this is a bijection, take some arrow, take some arrow F in your codomain CB comma A, which is the image of some element of GB. We note that we assume GB is non-empty, right? We did assume GB is non-empty. So elements of GB under this map will also have images. We take one such image. Okay, so take some element F in your codomain, which is the image of some element of the non-empty set GB. We have assumed that GB is non-empty. GB. So F here is an arrow B to A. We are working with this arrow. We are applying the naturality on this arrow, or rather its corresponding arrow in the opposite category. Yeah, so if you apply alpha B on this, note that this was our map alpha B, and what does alpha B do? Alpha B is a bijection, right? Sends elements of this to elements of this. What was F? F was exactly some element which is the image of some element in GB, right? Since this square commutes, so since the square commutes, what you essentially have is, since the square commutes, alpha B applied on FF of alpha A inverse of 1A, whatever this element is, doesn't matter, is equal to F. This is what you have. But alpha B is a bijection, and what was our f? This element f in your codomain was chosen in such a way that, so f was that particular, was some element which was the image of some element of GB, but this is an element of f, this is an element of FB, right? This element is entirely an element of FB. So what we essentially have is there are two different elements of your domain. One is an element of FB, one is an element of GB, both of which are getting mapped to F, which contradicts the fact that alpha B should be an injection in particular, right? And that is your contradiction. So since the square commutes, we have this. Now you note that, you note simply this: f in CB comma A was chosen to be the image of some element of GB. That was how we chose F, right? That was how we decided on F. Okay, so we take some arrow F in CBA, which is the image of some element of the non-empty set GB. Okay, but this element FF of alpha A inverse of 1A, this element is entirely an element in FB. Why? Because alpha A inverse of 1A is an element in FA, right? And when you apply your coproduct map on this element, you should arrive at just an element of FB only. That is how this is entirely defined. So this, all of these problems are arising because we initially assumed that alpha A inverse of 1A is in FA. Okay. So this is in FB. This is an element of FB. So this contradicts. Yeah. So was chosen to be the image of some element of GB under the map alpha B. And here we are seeing that alpha B applied on some element of FB is F. So this contradicts the fact that alpha B is a bijection, in particular an injection. Is an injection. And that ends the proof. So GB has to be empty for all objects B in C op. So G has to be the constant functor on the empty set. And that finishes the proof. We could do this again using the NPTEL MA as well. There is a shorter proof or an alternate proof. Let me just add that to it. I will not mention the proof. I'll just add a remark here that come up with a shorter proof using the NPTEL MA. But we didn't mention that proof because I mean, there are some things that could be a problem, a bit of a problem. Yeah, so that's all for this week. I believe the lecture was a bit heavy today, and also because I had to repeat a lot of things, which is why I again request you to please look at the lectures before you come. And yeah, let me stop the recording.